Hello everyone, my name is Sulakan Randil. So today in this video, I am explaining what I did in the project Human Activity Recognition System using deep learning. So the objective of this project is to classify human activities using multi-sensor accelerometer data. The dataset contains sensor readings collected from 5 accelerometers, and each sensor provides X, Y, Z axis values, resulting in 15 features per time steps. So the activities included in the dataset are cycling, push-up, walk, run, squat, and table tennis. So in this video, I'll briefly explain the dataset, pre-processing steps, deep learning models I have used, and the results I have got, and the deployed application on Hugging Face spaces. So what I have done first here is importing all the necessary libraries and dependencies for the project, and then I loaded the dataset from the Google Drive using drive.mount function, and then we go for the initial data exploration to get an idea of how the data is spread and how the data set is looks like. In the data cleaning process, what I have done is I have removed the missing values. So here we can see that after removing missing values, the data points have been reduced, and also I have removed the duplicates in the data set, and also the data type verification I have done here. And also, as machine learning models can't directly deal with text data, I have encoded the labels to the activity column, and also in the data set we have to check the activity distribution. So in the result we can see there are a high number of data points in table tennis and cycling than the other activities. So the task distribution in the data set is unbalanced, so we will have to take care of that too, because the model will be biased uh, if we train the data set in the same manner. And here it shows the feature correlation heat map, and these low colors show that there are no much of extremely high real correlation between features. There are only few show that a moderate correlation. So which means each feature contribute useful to the model. So that's what I have done in the processing part. So in this section, what I have done is generating overlapping sequences. So here the raw sensor readings are converted into sequence of consecutive time steps, which will be used as input to the deep learning model. So I selected k value as 20. Since the sensor sampling rate is 40 hertz, it corresponds to approximately 500 milliseconds of the motion data. To increase the number of training sample and preserve the motion continuity, so I have used 50% overlapping sequences, meaning each new sequence start 10 rows after the previous one. So the generate sequence function create sequence by taking k consecutive rows, here 20 as sensor features, and treating them as one training instance. Before generating these sequences, I have split the dataset into training, validation, and test sets using the temporal split. For each activity, the first 64% of the data is used for training, and next 16 for validation, and the last 20 for testing. This split is done before the sequence generation to prevent prevent data leakage. So if the sequence was generated first and then split randomly, the overlapping sequences would share the same sensor readings across different datasets, which would lead to overfitting model. So it happened to me previously, because I have done the sequence generation to the whole dataset and then perform the train split, and I got a really high accuracy, like 99%. And also so I came across this solution for that. Uh, First, split the data in each activity, and also while preserving the uh, temporal order, and then performing the uh, sequence generation. In this step, I applied feature scaling using standard scaler to normalize the sensor reading. Since the accelerometer values are different axes, it may have different ranges and magnitude. Scaling helps to ensure that all features have contributed equally during the model training. So the standard scaler standardizes the data by transforming each feature to have a mean of 0 and standard deviation of 1. This is the most important part section of the project, so building the model. In this section, I built the deep learning model used for the activity classification. So after researching for what kind of deep learning model is most suitable for this kind of temporal data of activities, so I came across the solution of hybrid CNN and bidirectional LSTM architecture, which works well with time series sensor data like accelerometer signals. So first, the CNN layers are used to extract the local motion patterns from the raw sensor readings, and then these layers basically work as feature extractors and help detecting short-term patterns, such as sudden changes in acceleration. After that, I use bidirectional LSTM layers to capture the temporal relationship in the sequence. So because LSTM is bidirectional, it processes the sequence in both forward and backward directions, which helps the model better understand the motion pattern over time. So finally, the extracted features go through the dense layers and softmax output layer, is used to classify the sequence into six activities, one of the six activities. During the training, I used early stopping and model checkpoints as callbacks. Uh, early stop, early stops. Uh, the training process if the validation performance stops improving, which helps preventing overfitting. And model checkpoint is used to save the best performing model during training. And the data set is, as I have mentioned earlier, the data set is not previously balanced, perfectly balanced, since activities like table tennis and cycling have more samples, and while activities such as push-up and have fewer samples. To handle these, I computed the class list using uh, balance strategy, and uh, these weights give a more importance to the minority classes during training. So the model does not become a bias because of the data imbalance. So the model was trained up to 100 epochs with batch size of 64. As we can see the training logs, the model quickly achieved a very high training accuracy, and the validation accuracy also stays high, which shows that the model is learning meaningful motion patterns from the sensor data. After the training process is completed, I did the evaluation of the trained model. So loaded the best saved model and evaluate it on the test dataset, which contains completely uh, in unseen data, and the model achieved a test accuracy of 91.92, which shows it is a high accuracy, and model can correctly classify most of the activities in sequence. So here we can see the test loss is also a very low value like 0.6692, and this shows the classification report. And uh, in overall, it has most of the values above the zero point 0.9. So overall, the model performs well across all activities. Uh, like activities such as push-up and squats show a very high performance because their motion pattern might be quite distinctive, like sudden change in motions, and some small confusions occurred in activities like cycling and table tennis, maybe because of the activity. These two activities are complicated, has some complicated movements. So, or the overall macro and weighted F1 scores are around 0.9 and 92 to 0.93. So, it confirms that the model performs consistently well across the different activities. Here I have visualized the model accuracies and the model loss. Yeah, these values are all above the zero point 0.9 value. Even though there are small fluctuation, this shows that model has a high accuracy, and model whi- which means the model can predict activity successfully. And here can see the model loss. And next we have the confusion metrics, and we can see most of the predictions of the model are correct. And as I mentioned previously, cycling and table tennis have some confused false predictions. Overall, the trading and validation graphs show that model learns effectively, and the confusion metrics confirm that it can accurately classify the most physical activities with a strong performance. So next, let's move to the bonus task, which finds the best pair of sensors to give the best performance in activity reconstruction. So here, after thinking for some time, what I came across is testing sensor pairs in the same model I used in the previous. So for each pair, I trained a CNN by LSTM model, which I used in the previous parts, and I used it and trained and evaluated on the same train validation test plate. Uh, the pair with highest test accuracy was the pair with highest test accuracy I selected as the optimal sensor combination. So here I did the same test plate and test plates and train the model. So I used a different scaler, uh, which fits the six features only column because we have two sensors, and then each sensor has three data. So in for a pair there are six features. So after testing all pairs of sensors, uh, I came across this result. So sensor one and two shows the highest accuracy, 94.38, and sensor one and three shows the 94.08 accuracy. So these are the results I got, and the best pair is I get the best pair sensor one and sensor two. So here is it shows the performance comparison of each sensor. So as the final task, what I did is saving the model for Hugging Space. So first first I saved the train model using .kras format, which stores the model in architecture, weights, and training configuration. This allows the model to be easily loaded for the deployment. And then I created the label uh, info.json file. So this file store the important metadata such as class labels, sequence length k, and uh, feature columns used during the training. After that, I downloaded the required files, scalar, label information, and trail model, and uploaded it to the Hugging Face space for deployment. So what I did was uh, import those files to the Hugging Face space and make app.py radio using radio resource, which we can test the machine learning model using a GUI, and here's the output of that GUI. We can upload the CSV file and predict the activity. As an example, if I show, we can upload the CSV file containing 20 sequence data uh, at least, and then we can predict the activity. So here we can see that if we upload the data, it is predicting the values correctly. Here we have got 99.9, 99.6 accuracy for the squad. So that's the overall project I have done.